We're going to talk about this topic of rotational dynamics and now Newton's second law in rotation. And again, you're going to see everything. Today, the problem that we're going to do has every single topic that we've done in the whole course. Okay? I could have put that on your exam, but I didn't. Speaking of the exam, you guys did great. This is perfect. This is exactly what we look for. If you look at the other classes the other people taking Physics 2A, you will not see as good performance, actually. We did the best of all three classes. What's that? No one got 100. Yes, that's one good thing. This test was well designed. There was not a single perfect score on the exam. That's what I always look for. The mean was about a 66 or so. This is exactly what we look for. If you talk to your colleagues in the other two sections, you'll see that on the first exam, for instance, the mean was somewhere in the 20s. In one of the other sections, we did much better than that. You'll see for the second exam in the other sections, they see something a bit worse. So you guys are actually you're outperforming on average the other sections. Okay? So this to me is a perfect distribution. You're all doing well. There's no one that I'm particularly scared about on this exam. Okay? Oh, yeah, by the way, our grades would not be posted yet. I still have a few makeup exams to give. Here's what you'll have. By Tuesday afternoon, you'll have your grade on iLearn. Wednesday in section, you'll get the exam back and you'll be able to see all the results. Okay? So by Tuesday afternoon, you'll know where you stand on this thing. And by the way, there's a few more people that have to go into the distribution, but it shouldn't change it much. Why is everybody so sad? This is great. How many people finished early? Where are my early finishers on these? Yeah. See, that meant it was too easy. No, okay. No, all right. Okay, that's in the past. That's like an old boyfriend or girlfriend. You don't want to think about it. You got to move on. You have a lot to do. So here we go. We've got to move up pretty efficiently over the next couple of weeks. So we're going to finish this topic that we've already started, which is Newton's second law for rotation. You'll see a lot of familiar topics. And then we're going to introduce this thing that is the rotational equivalent of mass, or something called the moment of inertia. It sounds complicated, but it's actually a really simple topic, so we'll just cover it. But before we do, let's just refresh. I bet a lot of you will do well on this time. So torque on a wheel. Oh, in fact, there was a problem like this on the test. There's a pivot with a rod, and it said which one of these torques will rotate it in the right direction. It was something like 93% of you got that one right. Yes! Good. So let's do this one. Which third force on the wheel applied at point P will make the net torque 0? So meaning, if this one is trying to rotate it counterclockwise, what do I have to do to rotate it clockwise with the same magnitude of torque? Okay? So take about 30 seconds. This is the same exact problem we ended with on Wednesday. So about 15 more seconds. Okay, 5, 4, 3, 2, get your responses in, last second. Okay. Let's come back. 77% said E. This is the right answer. You need twice the force because you're at half the radius to give the same magnitude of the torque. Do you see that both this force and the one that points up here are perpendicular to the radial vector? This is what maximizes our torque. Okay? So we're going to come back to this. We'll solve some of these more explicitly. If you didn't get this one, I think you'll see an example that looks a lot like it. Let's come back to where we started. Here's week 2 of our course. We talked about linear motion. We had position, we had its time derivative called velocity, and we had its derivative of the velocity called the acceleration. And you remember that these were vector quantities. So we went through a lot of hard work to understand vectors, to be able to add, subtract, and manipulate. Now, recently, last week, a little bit longer than that ago, we basically introduced three very similar parameters. Theta, which was the angle through a circle. There was the angular velocity, which asks how that angle changes in time. And then there's the acceleration, which is how the velocity changes. Do you see that we now have kind of a set of sophistication? There's a match here, right? These concepts are very much related. Okay? So this is just review. We now get a bit of an understanding. And just like our linear kinematic equations, we could write down rotational ones. This was actually a much less accurately answered question on the exam. There's one about a mud skipper on a merry-go-round. We're going to see that problem come up again in our life. But basically what it did is it forced you to use these same equations to understand accelerations, velocities, and displacements, but in the rotational coordinates. So angular displacements, angular velocities, and angular accelerations. Yeah?
So then how do we switch from rotational to linear?
So we've done this already. I won't show it here, but you'll see it in the example. It's basically related by the radius. So if you remember, the S theta is equal to the displacement is equal to basically r theta, right? We talked about this. The velocity is equal to r times the angular velocity. The acceleration is equal to r times the angular acceleration. We'll see it in the example, but that's how you relate those two things. Okay? So this again is review, but we're going to see it in our problem. And then we moved on to Newton's laws. I'm only going to highlight this one for now. So when I talk about Newton's second law, this is the one that applies only to a single object. You remember? Right? Newton's third law told us how to relate them, but this one is for each body. I want to actually focus, we have had tons of practice with this, but I want to focus on this part, this version of how we write it. Okay? So if you look at what this means, if I wanted to accelerate an object, okay, did you ever hear of the word inertia? If an object has a lot of inertia, what does that mean about the object? It's hard to change. It's heavy. It's hard to change its direction, or it's hard to change what it's doing, right? Like if you say someone, oh, that person really has a lot of inertia, it means like I can't change their minds. Okay, they're hard to change. Do you see in this equation? Let's call this thing mass. Let's call it inertia for a moment. In fact, that's what Newton called it. If you have an object that has a very large inertia or a very large mass, for a fixed force, it's hard to accelerate. Do you see that if m is really big, the acceleration is really small if you're a constant force? So I'm just going to use this language of inertia to replace what we call mass. So if I have 10 newtons of force that I can use. If I have a very high inertia object that I'm trying to move, I'm going to accelerate it only a small amount. Okay? And you'll see why we call it this in a second, but this is the language that Newton used, inertia instead of mass. And now this is the new part. So this is where we're getting into the new topic. We're going to use this to solve some examples today, but you can take, if you look at Newton's law that I just drew you, right? We've seen this before. The acceleration is just the sum of forces over m. I can write down the same exact equation, but for rotational coordinates. Okay? And what we need is something that acts like mass in a rotational system. And in this rotational coordinate, it's this thing called the moment of inertia. So I'm going to define it first, how to calculate it in certain objects, and then we'll use it. So this thing I is called the moment of inertia. Objects with larger moments of inertia are harder to get rotated. Does this sound familiar? When we just said with Newton's second law, objects with larger inertia are harder to accelerate in a line. Objects with larger moments of inertia, or the rotational equivalent of inertia, are also harder to get rotated. Okay, so there's a relationship if we know this language carefully. Now, what I can do, if I want to solve the acceleration of a rotating object, let's say this wheel, I basically have to know two things acting on this wheel. I have to know what the torques are acting on this wheel, and I have to know the moments of inertia. And the moments of inertia are defined as all the masses, so I can sum up all the points of mass on the object and how far they are away from the center. Okay? You'll see it's a complicated object in a lot of cases. We'll do some simple ones. But if I know what the torques and the moments of inertia are, I can tell you exactly what the angular acceleration will be. So in this case, when I let this go, will it have a positive or negative torque on it? Negative torque, right? We said that counterclockwise is positive. So I would argue that I would have a negative acceleration, right? Based on this, if I have a negative torque, that means that I have a negative angular acceleration. If I let go, the mass drops. This thing rotates in that same direction. Okay? So we're going to see how to relate these with this thing that looks like mass. And here's what we'll see. Okay? What I have to do to calculate this is I have to start at the axis in either of these two examples. I have to go to every point of mass in that object and add up at that point of mass, how far is it from the radius squared? And I go through and I add every little bit of mass that makes up this wheel. But here's the general rule, and I'll show you examples of this, so you'll see this a lot. But when I have mass that's concentrated near the axis, so near the center of rotation, I will have a much smaller moment of inertia. So it's equivalent to like a small mass. If I have a smaller moment of inertia, that means I can accelerate it more easily with a torque. Okay? And if the mass is really far out, so look at this one where it's just a ring of mass far from the axis, that's a larger moment of inertia. This is an object that is harder to move. All right? So this is basically how we calculate it. Does everybody understand this sum sign? Okay? It means that if I have points that I'm adding up, I just add up these little pieces. Here's mass 1 times its radius squared. Here's mass 2 times its radius squared, etc. And you kick this around the point. So what we'll do is we'll work through an example where we can ask about forces, torques, accelerations, and angular accelerations. And we can relate all of these using kinematics and all of those equations we just said. So just to see if we get it, keep an eye on this equation. So everybody look at this equation. Write it down in your notes. Have it right in front of you. Sum of mi r squared. See if you can solve this problem. Okay, so here's the next problem. This is just basically calculating that moment of inertia in two cases. So go ahead with the people next to you. Have this equation in front of you. Which of these dumbbells has the larger moment of inertia around the midpoint of the rod? Okay. So I have two rods. The masses at the end are m/2. And I say right here that the rod itself, you don't have to worry about the mass. Okay. So if you look at that equation, what it does is it adds 1 m times r squared and then the other m times r squared. So see if you can calculate this. So here's the expression that we'll use. So see if you can add these pieces to find the total moment of inertia. So take about 30 more seconds. See if you can do this. Okay, I'm going to pause this. Let me pause. Here's what I'm going to do. Let's solve the moment of inertia for the one on the left, just to make sure we understand how this works. Okay? So if I have a sum, how many masses are there in the picture on the left? There are 2. What are the values of those masses? Just m. Okay? And what's the center point? What's the distance from the center point to one of those masses? What's it? Well, it's not r because of the way they're drawn, right? So if this whole length is r, what's the distance from the middle to the outer edge? It's r/2. Okay, so I have mass plus. You see how I got that? I added one mass, the one on the left. It's at a distance r/2 from the center. I had a second mass, the one on the right, and they just add together. Does that make sense? Now I can simplify this a little bit because it's all the same answer. So I get something like 2 r squared over 4, or mr squared over 2. Does that make sense? Okay. Now, tell me, do the same basic calculation and see which is bigger, this one or the one on the right. So now I've redelivered this problem. Just do the same careful calculation. This one, the distance from the center to the edge is r in this case. But the masses are also different. So calculate this one and tell me which one is, what did I ask? Which one is larger moment of inertia? Okay, so take about 20 more seconds. Okay, about 5 seconds. There's a whole bunch of responses left. Okay, I'm going to stop it. Okay, here's what I said. All I did on the board was I relabeled this one to call it A, so that when I write it on the other side, I call it B. Straight. So we said that this one on the left, was mr squared over 2. Okay, let's just add. Let's do the other side. The answer I got the majority of. Maybe I'll tell you in a second, but let's just see what it is. Did everybody get that for their first piece? Right? There's each mass is now m over 2, and I have it at a radius r from the center because I'm dividing that line in half. And so it looks like I get 1/2 plus 1/2. This gives me mr squared. Okay? So which of these is the larger moment of inertia? It's the B. It's the one that we just did. And so the answer is B, which about 65% of you said. Okay? So all you have to do when you have these calculations, you just calculate. I take the mass times the radius squared, and I add up all the pieces. Okay? Now, what did I say? Which of these, if I was given a constant torque, just I had some amount of torque that I could apply to the system, which one did I say would be harder to move? Right? Let's go back even a step further. If I had a giant heavy table versus a light table with low mass, which one would be harder to move? The one with a larger inertia or mass. So in this case, which of these would be harder to give an angular acceleration to? The one with the larger moment of inertia. Which one had the larger moment of inertia? It was B. Okay? So what we will find, and we'll work through some of this as examples, is that the distance from the axis can generally be more important than the mass. If I have very small masses that are really far away, do you see that this goes as r squared? Our equation goes as r squared. The radius increases the moment of inertia faster than the mass. And so small objects far away will actually be harder to accelerate. Their moment of inertia will be larger. So here's what you'll find in the book. And I don't expect you to calculate any of these because they're kind of, if you've taken a calculus course, you may have actually done this. But here's a couple examples for problems that you'll see in the homework. So let's say I just had a thin rod that's rotating around this axis point. It just has a weird factor in front of it. It's 1/2 ml squared, where L is twice the radius. Okay? You can actually go through. You can solve some of these very simply. This one, and most of these require integration, but you can do it. But here's another example. If I have a solid disk of radius r, I see that its moment of inertia comes out to 1/2 mr squared, whereas a hollow disk where all of that mass is out at the edge, it only gives me a factor of mr squared. So which of these would be harder to accelerate? Which one? The hollow one. When you have a larger moment of inertia, you're going to have a harder time giving an angular acceleration. Okay? We're going to see that come back next lecture, but we won't get too much into it now. So now you see that we have this we've created all of this kind of knowledge about how to solve these problems of forces, how to understand accelerations, velocities, and displacements. And now we see that there's a rotational equivalent to all of this. And so we're going to combine all of this in one big kind of nasty mega example today. But here's the thing, if you remember, we summed up all the forces to get basically applying Newton's second law. Now we're going to look at how we sum up all the torques. Before we looked at mass or inertia, we said that if I have a higher mass or a higher inertia, it's harder to accelerate. Now we have this thing called the moment of inertia. And then if you look at acceleration, we know that we have angular acceleration. But here's the most important part, is that Newton's second law applies in both, just with these radial coordinates. So Newton's second law from before gave us an acceleration that was the sum of all forces divided by the inertia. In rotation, the angular acceleration is the sum of all torques divided by the moment of inertia. Okay? Do you see now that we have this whole system that you're going to have to solve lots of problems from, in particular on the final? So how do we deal with this? What's the first thing we do? Any problem we ever solve, what is the first thing I tell you to do? Before you draw, you imagine what's going to move. Okay? You just think about what is moving. This is called classical mechanics. Dynamics. We're looking at things that are moving. So the first thing, even before you draw a picture, is just to imagine, okay, I have a story that I've been given in my exam and has some tuna fish in a box. How do I draw this as a moving diagram? Okay? Then you go and you draw a picture and identify the axis about which the object rotates. So this is now rotational motion. After you've drawn that picture and imagined the motion, you then, just like you did in Newton's laws, you identify the forces and determine their distance from the axis. Okay? And you can assign a lot of these coordinates if you have to. Then you calculate the torques caused by each of these forces. Remember how to calculate torques? It's the radius times the perpendicular component of the force. And then you find the signs of the torques. Which direction will a positive torque rotate an object? Counterclockwise. Okay? So if I have a counterclockwise rotation due to a particular torque, that's positive. If it rotates it clockwise, that's going to be negative. And then, this is the little extra piece that we now have to add, is we have to find the moment of inertia and go back to kinematics to find angular positions, angular velocities, angular accelerations. Okay? What if I ask you for a linear velocity or acceleration? You then have to relate these angular ones to the linear ones. You see that this has basically everything from week 1 through 7 in it? I can give you one problem, and I'm going to in a second, that basically requires knowledge of every single topic that we've studied. Okay? It doesn't seem that way, but it will. Let's study for a moment the trebuchet. This is the pinnacle of medieval weaponry. Okay? This was basically one of the most incredible and complicated devices that the medieval era basically created. Okay? Who knows how a trebuchet works, just judging from this picture? These are actually old plans, basically, for how to build a trebuchet. All the lengths that you should build, all the lengths and angles. Here's how a trebuchet works. I basically take a big basket and I fill it with a humongous weight of rocks. Okay? Then I put, where the pivot is this point A, where this long rod basically pivots about that axis. Okay? Then I take a little basket with a rope and I put a big rock in that side too, just one big rock. Or sometimes, what they used to do is put in a rancid, dying, or dead cow. Okay? Or the other one is pit. Does anybody know what pit is? It's big flaming tar. That was one of their other favorites. They would take a big ball of flaming tar and shoot it at somebody's castle. Okay? So this was real. I mean, I'm just telling history. But what you would do is you would basically pull, there's a crank here that pulls this arm down. There's a whole bunch of people that slowly pull this down. They set a little clip. This lifts up. What do you think happens when they pull the clip? The weight, the big heavy part drops. The light part, this little rock in the basket, goes flying really far. And the dead cow that's in that basket poisons the whole community hiding inside the castle. Right? That was the intent. It's gory, but true. So here is this kind of medieval weapon. Let's see if we can simplify this quite a bit. And I did this last time. Let me show you. Let's make this one really. Do the heavy one first. This is kind of scary. Okay. Here we go. I'm going to take this one off. This one off. Okay. Shield your eyes. Okay. What's going to happen when I let this go? This is 20 grams. That's, I think, a kilo. That's 1,000 grams. Okay? What's going to happen to this system when I let it go? Which way is it going to rotate? Positive rotation. Right? It's going to rotate this way. What would you say right now about the sum of forces on the object right now? If I add up all the forces on the object, what would I say about it? Zero. Why? Because my hand's there and it's not doing what? Accelerating. Okay? What would you say about the sum of all the torques right now? Zero. Why? Because there's no angular acceleration. You see that? It's just like Newton's laws. Now, the moment I let go, which direction will it rotate? Positive. What would you say about the sum of all torques in that case? No longer zero. They have to be positive. Okay? Let's see what happens. Let's just watch. Nick, shield your eyes. For real. Good. I didn't want it to actually launch. Did you see what happened? The heavy side drops. That side flipped off the side of it because I didn't want it to actually shoot Nick in the head. Okay? But which way did it accelerate? To the positive direction. You can ask very simple questions about this system. If I let that mass stay on, what would happen to it? As I fling up towards the top, where would it go? It would eventually throw and turn into 2D projectile motion. We're not going to solve that part of the problem, but we could. I could make one exam problem out of this simple trebuchet, okay? But I'm not. I won't do that. But let's ask a very simple question about this and see if we can work through one of these problems piece by piece. Again, this is a... actually, let me leave it up on one so that we have the picture. We don't really need the picture, but I'll leave it. Let's leave it on the right. So here is what I would call a simple catapult. Okay? I'm going to, instead of solving the trebuchet problem, which is really complicated, I basically have reduced it to this ruler that is 200 centimeters long. There was a light mass here of 20 grams and a heavy mass there, and it flipped the masses to shoot the whole thing across the room. Okay? So here's a question I could ask on an exam. And it's a very simple question, but it turns out that it's actually quite hard to solve this problem. We're going to work through it very carefully. So let's say in this system, and I can even draw, let me redraw a picture just to show you what it looks like. There's my pivot right in the middle, so it's kind of fixed on some holder. Both of these masses are at equal radius. That's to make life a little bit easier. And I have two of them. I have a very heavy one. That was the 1 kilogram. And then I have a very light one, which was 20 grams. Okay? I can ask two really simply stated questions that turn out being everything we know in this class. So if this mass is bigger than this one, what is the linear acceleration of m, the little one, when I let go of the catapult? Okay? What is the linear acceleration that m undergoes at the instant I let go of the catapult? Okay? Now the other thing I could ask is what is the velocity of little m when theta equals 90 degrees? This is the question that would actually ask, what's the velocity when I let go of this thing? So you can imagine I launched this thing, little m is right at the end, and right there, I launched little m at Nick. Okay? I could ask, these are two really easily asked questions that turn out they're quite hard to answer. What is the linear acceleration of little m, and what is tangential velocity at this angle, 90 degrees? So what angle does little m start at in our rotational coordinate system? 0, and then it goes through theta equals 90. Okay? So let's first, can everybody imagine the motion? If I gave you this picture, could you imagine the motion? Sure. Mass m drops, little one flies, this thing goes flying across the room when it lets go. Okay? So we got that part, we've even drawn a picture. And the first thing we're going to do, again, is come back to Newton's second law. So the very first thing we do is write down Newton's second law of dynamics. But this is now written in rotational coordinates. So the sum of all torque in the problem is equal to the moment of inertia times the angular acceleration. You see that this is just like mass times acceleration. We just now introduce these rotational coordinates. So everybody's okay with that. That's Newton's second law. We just wrote it down. We haven't done any math. Now the first step, I want to make sure we get this, so let me cover up even this piece so that we don't get distracted. The net torque, we already said this, the net torque on this object has to be what direction for it to spin this way? It has to be positive. Okay, we know that. Which of these torques, so I have the heavy mass trying to pull down and flip it that way. That's a positive torque because it's trying to rotate it this way. What's the little mass doing? If that big mass wasn't there, what would the little mass do? It would try to rotate it the other way. Right? It would try to rotate it in the negative direction. So each of these torques, I imagine, no other forces are acting. What would the torque be due to that individual force? So this would be a positive torque because it would rotate counterclockwise. The little mass would want to rotate it the other way if that big mass wasn't there. Now the sum of those torques, I can write down explicitly. Remember that torque is just the radius times the perpendicular force. Let me zoom in a little bit. We don't need too much of the diagram anymore, but I'll try to save it. Okay. So the torque is the radius from the pivot times the perpendicular force, and I just labeled this for the big mass and for the little mass, and I've now written down the sign. One will rotate them in the positive, one will rotate them in the negative. And then I can just write these down. What is the force that this mass is applying to this ruler? It's just the force of weight. Weight is equal to mass times little g. So I have the radius r, I have little m times g, but that one's negative, and I have the big mass at a radius r, which is a positive quantity. Does everybody see? That's a pretty straightforward application. I have two forces, their weight of each of the two masses, and I've kept track of the sign of the torque. Okay? Remember, torque is r times the perpendicular force. There are no angles in this problem to complicate it. It's already complicated enough. So I can just simplify this a little bit by taking out the radius and g, just kind of doing some algebra, and I get m, big M minus little m. That's the sum of all torque. Okay? Now if I go back, I got the sum of all torque written down. Now I need this I times alpha, but first I need to solve this thing called moment of inertia. Yeah?
What's the difference between little r and big R?
Well, little r is how we would write it generically, so I keep that kind of as a generic coordinate. In this problem, I've drawn the actual dimension as big R. This is how you'll see it in the homework in the textbook a lot too. So the little r is basically an algebraic coordinate. The big R is actually what the real length is. Okay? So now I have to find this thing called the moment of inertia. And this is what you just have to calculate. Right? You can't know this thing beforehand. So remember, the moment of inertia is the sum of all masses times their squared radius, each point. And in this problem, there's only two. It's a pretty easy problem. So I have the little mass at a radius r. Again, going back to the picture. You can see that the little mass is at a radius r, so it's mr squared, because of the way the moment of inertia is calculated. And then I have the big mass at another big R squared. And I just add them together. So I get big M plus little m R squared. Okay? So I found the sum of all torques. I found the moment of inertia. And now I can actually solve for the angular acceleration. So here, I can combine these to give, remember, acceleration is just the net torque over I. So I take the first equation, that was this one, rg m minus m. It's here. And then I divide it by I, which I just solved, m plus m over r squared. And then I cancel out a couple terms. I think I just canceled one r. And so you get g over r times the difference in the mass over the sum of the mass. It's a complicated thing, but is there any question about the algebra? This was pretty straightforward so far. We summed up all the torque. We summed up the moment of inertia. We've now solved for angular acceleration. What would we ask for, though? The tangential acceleration, right? This is the angular acceleration. So if you remember, if I know the angular acceleration, which I've just written down, I can find the tangential. This actually was the question that came up earlier. The tangential acceleration of that little mass is going to be its radius from the pivot times the angular acceleration. Okay? It's an r distance r away, and so I can calculate this. If you thought that algebra so far was tricky, wait till you see where we go next. Oh, does anyone ever see The Hobbit? I hear like Gollum noises every once in a while. He hates it. He hates it forever. He hates it forever. Baggins is. Okay. So let's try to follow through this and finish it before we go. We know that the tangential acceleration is equal to the radius times the angular acceleration. And I plug that in. R times alpha. I write this expression for alpha times r cancels so that I end up with a really simple expression for the tangential acceleration. The tangential acceleration of that little mass as it gets thrown around this circle is g times m minus m over m plus m. What are the dimensions of acceleration? What are the units of an acceleration? Meters per second squared, right? What are the units of this expression on the right? Meters per second squared. The mass is, even though you have this effectively reduced mass, that dimension basically cancels. You get g, okay? So that's our first answer. Let me see if I actually, yeah, there, I put a box around it, right? The first question was, what's the tangential acceleration? We had to go through finding all the torques, finding the moment of inertia, solving for angular acceleration, and then converting it into a linear or tangential acceleration. And that gave us this expression. Now let's just do a sanity check. Remember, we had a big mass. Yeah, you're probably all lost it, right? We had a big mass on this side and a little mass on the other side. If the little mass is 0, what happens? If I have a giant mass on this side, the little mass is 0, what's the acceleration of this object going to be?
For every time.
It's going to be what? G, right? It's just going to go through free fall. So if m equals 0 in this equation, I see that the system basically accelerates through free fall. If m equals 0, little m equals 0, I just get big M over big M, that cancels. And I see that the big mass just falls normally as you would expect. Okay? Now, the other piece I can ask is, what if little m is exactly the same as big M? What if I have two big masses, one on each side, same radius away? How will the system accelerate? It won't, right? It's in equilibrium. So let's see if that works. If I say m is equal to big M, I see that I get big M minus big M is equal to 0. The system won't accelerate. What do we say about a system that has no rotational acceleration? It's in equilibrium. Good. We'll come back to that next time with C.T. Fletcher and Arnold Schwarzenegger. That's next lecture. Okay? Now, here's the harder part of the question. And we're going to answer this. What was the second part of the question? I know it's acceleration. Now I ask, what is its velocity as it reaches 90 degrees? Okay? So this thing started here with what velocity? When I was holding it, what was its initial velocity? 0. And then what happened? It accelerates, accelerates, accelerates. I'm asking, which direction is the acceleration? I saw a good one. Which direction is that velocity going to be? straight this way. It's tangent to the circle. So when this point reaches 90 degrees, just like we said before, it's tangent to the circle. So here's where we have to use kinematics. So the question is, what is the velocity at 90 degrees? Do you remember these problems in 2D projectile motion where we said we shoot a projectile and we ask how far it goes? You see that I didn't include that part, but I could, right? Find the velocity, then find how far it goes, right? This problem could just be, seriously, one big exam, and I would force you to build a real trebuchet. But let's just look at it. Let's go to kinematics. When we think about velocities and displacements, we need kinematics. So first, I'm going to start with the angular form of our kinematics equation. Theta final minus theta initial is just the angular velocity times the time plus 1/2 angular acceleration times squared. Does this look familiar? It looks exactly like the linear form, but we just are now using angular coordinates. So the first thing I'm going to do is I need to find the final velocity, but this tells me how much time this thing goes through. So what is theta final minus theta initial? How many degrees? 90, right? Theta initial was 0, theta final was 90. So I'm not going to plug that number in, I'll just keep it as a character, an algebraic expression. But I basically just solve for delta t. 2 times the difference in angle divided by the angular acceleration, square root the whole thing, and I get the time it takes. I didn't ask this question, but we need it. It's the time it takes to rotate through 90 degrees. Okay? Then I can find the velocity. This is just like an old-fashioned kinematics problem. You guys are like experts at this, I'm sure. You could do this part in your sleep. Now I find the angular velocities. The final angular velocity is equal to the initial angular velocity, which I said was 0, plus the angular acceleration, which we just solved, times the amount of time which we just solved. And if I write that down, I get alpha square root of 2 delta theta over alpha. Here's an algebraic trick here. Let me write it so that you see it. You see that if I bring this alpha into the square root, it's alpha squared times 2 delta theta over alpha. Does everybody know that trick? If I basically take the square root of this alpha and pop out of the square root, but I can pop it back in, okay? This is just a common algebraic manipulation that basically allows us to simplify the answer. So the final angular velocity is equal to 2 alpha theta final minus theta initial. And then what is going to be the linear or tangential velocity? How do we find it from an angular velocity? We multiply it by r. Okay? So we know that the tangential velocity is r times omega. So the final tangential velocity at 90 degrees is big R times the square root of 2 alpha times delta theta. I plug that stuff in. Let you take a picture of it. I want you to work through this on your own. And I finally come to page 3 of this problem with the final answer. Okay. The final velocity tangent to the circle in this messy, complicated system, but with a very simple question, depends on a lot of different things, but it has almost all been reduced to information that I gave you. I gave you the radius, I gave you 90 degrees, you knew the 2 masses, they were just labeled m and little m, and you get this number g. Okay? Now a couple things about this. If m equals 0, you get the same answer. This thing doesn't have a velocity. Right? There's a whole bunch of ways of checking this. Now you might ask, why in the world did we just go through line by line so carefully through this problem? There are many reasons. One is, this problem has every piece of physics that you have been and will be tested upon. All very